What's up, folks? This is Chapter 2. We are only going to do Section B, which is on special number sets. Later on in the year, like many months from now, we might come back and chat again about interval notation, but that's not going to be until we cover inequalities. And the rest of this chapter, they're just not for our course. I love me a good Venn diagram. I got a lot to say about the topic, but it's not for us, so let's get going. Priority number 1 is I need you to be able to recognize and interpret the symbols. I'm sure many of you know a lot of the words that I'll be using, but the symbols might be new to you, and you'll be required to recognize those on assessments. And then secondly, hopefully you can use what you know about these different types of numbers to answer problems under the branch of mathematics that's called number theory, which we won't get deep into what that means. But you'll see some examples later on that'll give you an idea. So what are the number sets that we need to know? Here are the first bunch of them. This is not all of them. First up, we've got what's called the natural numbers. We also call them the counting numbers. And these are all of the numbers listed here. And it's an infinite in size. So we start at 0, then 1, 2, 3, 4, etc. We've got a list happening there, and we've got it kind of illustrated on a number line here. It's just where those red dots are. I think they're red. I'm colorblind. Anyways, those are the natural numbers. Now, if you are coming from an American education previous to this course, you might have learned that natural numbers start with 1 and that the whole numbers start with 0. And that's because the mathematical community can't agree on what definition they want to use. We're going to go with natural numbers begin with 0 in this course because that's what the IB does. And as I've said previously, this course is designed to get you into the IB higher level mathematics in a couple years. The next set we want to discuss are the integers. So that's all of the natural numbers, but then also their negatives. So this is also infinitely big. It goes forever to the right and to the left on the number line. And that brings us to our first really weird question for the day. Are there more integers than counting numbers? On the one hand, you might say, yeah, of course, because the integers contain all of the counting numbers, but then they also have all these extra ones. But on the other hand, I just said that they're both infinitely big. The answer is that they're the exact same size. No way am I going to try to explain that to you here, but if you're interested, you can research the guy whose name is on screen right now. He did a lot of really fascinating math with different sizes of infinity. Anyways, let's move on to the next one. We also can consider, instead of thinking of all of the integers, often we are interested in only the positive integers. So that's basically the natural numbers, except not including 0. And hopefully you know that 0 is not positive and it's not negative. So that's a pretty easy set to work out there. And then the last set that we have on screen are called the rational numbers. Rational numbers can be written in the form of a fraction. So we have here p over q is our fraction, where p and q are integers themselves. And of course, we note that q could not be equal to 0, because if it was, then we'd be dividing by 0 right here, and that would be a huge problem. Of course, we're never allowed to divide by 0. Rational numbers can also be written in the form of repeating decimals or terminating decimals. Terminating just means the decimal ends. So like on screen, we already have an example of that, 0.5. It's clearly a decimal number, and the decimal ends because there's no numbers after the 5. So that's a terminating decimal and a repeating decimal, like 1/3 is the same as 0.3 repeating, right? So those are all rational numbers. Now you've probably noticed those 4 symbols. I didn't mention them yet, so let's get these out of the way. In a quiz or an exam or in textbooks or wherever, you'll often see these symbols used as kind of a shorthand because mathematicians are very lazy and we do not like to write out words in full sentences if we can get away with it. We would rather just use, you know, a couple of symbols to get the idea across. So let's say we had a complicated equation later in the course and it has multiple solutions, because we'll certainly be dealing with plenty of those. Let's say further that I'm only interested in the integer solutions. So some are integers and some are rational numbers, some are decimals. If I only want the integers, I might say x is, and then rather than using the word x is an integer, I'll just say x is that symbol. And then you'll recognize, oh hey, that weird looking z, that means it's an integer. I might be even fancier, and I might use this symbol. It looks kind of like the euro currency symbol. That just means the same thing. That means x is in the set of integers. You're not required to write these symbols in any of your answers. You can always use words, but you do need to be able to recognize them when you see them on a page. If you're interested in where these symbols come from, like why are we using z and q? Because the n is pretty obvious, right? That n stands for natural. Okay. The z comes from the German word for numbers is Zahlen. So look at that. Now we're even learning foreign language in this video. That's cool. The positive integers, you'll see right here, we've got that little plus there. It kind of looks like a plus where an exponent might be. So that's just a symbol that means, yeah, I want the positive ones, right? Any guesses as to what that one means? Hopefully you figured out that's the negative integers. And then the last one, we've got this q, which comes from English again, and that's because we said rational numbers can be written as a fraction, and if fractions we know are division, and when we divide, we get a quotient. So that's where the q in rational numbers comes from. Now, if we ignore the positive integers for just a second, these sets are getting larger and larger, right? So we had the natural numbers, that was just 0, and then whole numbers moving out to the right of the number line. The integers includes all of the natural numbers, but then also has their negatives. The rational numbers, we don't put them on the number line because there's far too many of them, but that's going to fill in many of the gaps in between the integer values. But there's more. We also have, rather than being rational, we have these numbers called irrational numbers. So these are numbers that we can't write as fractions or as repeating decimals or as terminating decimals. So for example, if we have a surd, fancy word, don't worry about it. Basically, if we have a radical, so one of these symbols, and what's underneath it is not a square, a perfect square, it's irrational. So the square root of 2 is irrational. The square root of 7 is irrational. The square root of 3 is irrational. The square root of 4, well, that's 2, so that makes that rational. So only if we have a perfect square under there. For those of you who know about cubed roots, it will be rational only if the number underneath is a perfect cube. So the cubed root of 1 is rational, because the cube root of 1 is 1, but the cube root of 2 and 3 and 4 and 5 and 6 and 7 are all irrational. The cube root of 8, that's rational again, because the cube root of 8 is 2, and so on. So we also have some other really famous irrational numbers. Back over here on the left, we've got pi, because that's a decimal that never ends and never repeats. There's plenty of other irrational numbers out there like pi. Another famous mathematical number that you'll see, not in this course, but probably next year, is this number e. And we could also make other fancy looking decimals, like decimals with patterns. For example, the decimal 10, 110, 1110, 11110, and so on. That clearly has a pattern, but the pattern is not repeating. So that is an irrational number. There's no symbol for the irrational numbers. We don't use like a fancy looking capital I or anything. The only symbol that I could think of using is the Q from rationals, but with a little apostrophe next to it. Don't worry about that. I won't. That won't be showing up for us in our course. And finally, we have putting the rational numbers and the irrational numbers together. We get every single number that we could place on a number line, and we call these the real numbers. And that is a very sad name that they decided to call that the real numbers back in history. I really wish they hadn't. But that's a complaint for another time. The symbol for the real numbers is a fancy looking capital R. Obvious enough. And as I said, that's all of the rational numbers and all of the irrational numbers. They're all real. Some things are not considered real though. So 2 examples here. We can't divide by 0, as I said earlier. And certain types of radicals we can't compute. We can't take the square root of a negative, for example. I'd like to just visualize all this for a moment. So we have the natural numbers, fancy n, okay, and again, that's 0, 1, 2, and so on. Those are contained within the integers. So we add now -1, -2, -3, and so on. Those are all contained in the rationals, because obviously any of these numbers I've written down so far can be written as fractions, like -3/1. So clearly the integers are rational, but then the rationals include other things like 3/5 and whatever, 0.7 repeating and so on. And then on the other side of the screen, we've got our irrational numbers. So I said pi and e and the square root of 11 and so on. And put all of them together, and we get the real numbers. That kind of makes up everything here. This was our q, and this was our z. Now, I don't want you to get the wrong idea and think that this is all of the numbers that there are. Some of you might have heard of imaginary numbers. This is something you'll see in a future course, but imaginary numbers are what we get when we take the square root of -1, for example. This is why I said I was sad about the names, because imaginary numbers exist. Put the imaginary numbers and the real numbers together, and you get what's called the complex numbers. So there might be a few of you out there who have heard of these, but again, we're not going to touch this in our course. Oh, and by the way, there's more out there beyond the complex numbers. We have things like quaternions and octonions, and oh my gosh, this is so exciting. So that's the end of the first goal, all right? You just need to know what those symbols mean when you see them. And now I just want to do a few examples of number theory. So this is like playing around with the properties of these numbers and just, I don't know, like having fun with it. So for example, here we've got a repeating decimal 0.36. Now I told you that any repeating decimal is rational. So we already know that this is true. But here, let's actually show that we can write it as a fraction. Can we work out what fraction 0.36 repeating is? We can, and we can be kind of clever about this. So check this out. We're going to start by just using a variable, x, and x is going to equal this number that we're dealing with, 0.36. Now, there's 2 numbers here that are repeating. So what I want to do is I'm going to multiply x by 100, because that's 10 to the power of 2. And I think you'll see why in just a moment. So if I multiply x by 100, then 0.36 repeating becomes 36.36 repeating. Oh, that's very interesting. Notice that we could rewrite this as 36 plus that repeating decimal. And what we're going to do now is subtract. We're going to do 100x minus x. And 100x minus x is clearly going to be 99x. And when we subtract 36 this repeating decimal minus the repeating decimal, well, all that's left over is the 36, which means that x has to be equal to 36 over 99, which is equal to 4 over 11. We could do something very similar here, and this is going to bother many of you. We can use the same process to show that 0.9 repeating is exactly equal to 1. It's not close. It's not rounding it up to 1. They're the exact same number. So doing it the same way as before, we set x equal to 0.9 repeating. Now, that's only 1 digit repeating, so I'll do 10 times x. 10x is therefore 9.9 repeating. I subtract. 10x minus 1x is going to be 9x. 9.9 repeating minus 0.9 repeating is just equal to 9. Divide by 9, and clearly x is equal to 1. If you're not satisfied with that, I'll give you one more explanation as to why it's true. You know, I trust, that 0.3 repeating is equal to 1/3. Okay, if I multiply 0.3 repeating by 3, I get 0.9 repeating. If I multiply 1/3 by 3, I get 3/3, which is 1. So there's really no getting around it. For some of you, this is going to seem very obvious. You'll be very comfortable with it. That's great. I know there's going to be some of you who are going to really hate this and are going to think that I'm like lying to you or trying to trick you here. Trust me, it's true. I showed you on this screen a whole lot of different number sets, including some weird ones that you probably hadn't heard of down there. Of course, there's lots of other number sets out there. Prime numbers we discussed in the previous videos about exponents, and prime numbers go along with composite numbers. And then there's other numbers which are neither prime nor composite. I just discussed odds and evens, so that's another way to break up integers further. And then there's these other words that I'm sure you've never heard of: constructible numbers, algebraic, computable, and transcendental numbers. That's all getting like really advanced stuff, but it's neat to think about. And then we have things that are not numbers. So you can like make up things like that one, and infinity is not a number, so please don't think that it is. And there's probably other sets that I've left out of here, but this is just a list that I came up with. And I really wanted to make a point here that there are things that are not numbers. So like I said before, we have imaginary numbers, which they're not real, but they do exist. And then here we've got like 11 Brazilian, which is a made-up number, but it's not imaginary. So that hurts my head to think about. We definitely could have chosen better vocabulary for that in mathematics. Sorry. That's the end.